So for our last example, it's not going to be as straightforward as the ones that we've done. There's going to be an intermediate step. So what we're going to do as far as choosing a series to which to compare this, we're going to kind of mimic what we did previously. We're just going to look at the leading terms in the numerator and the denominator. So what we would get is kind of like a general or watered down look. So we would consider, like, say, n times 2 to the n over 4n cubed. And the reason we're doing that is because when we know when we're taking limits, adding a constant, especially as n's going to infinity, it doesn't play into the convergence or the divergence of a series or a sequence. So from here, I'm going to also omit the 4 as well, right? So I'm going to scrap the 4 because multiplying a limit by a scalar multiple, that's not really going to change the convergence or divergence either. So then what I would do is I would then simplify this. So I would really have 2 to the n over n squared. So just to be clear, the progression is this: n times 2 to the n over 4n cubed plus 1, kill the 1, n times 2 to the n over 4n cubed, kill the 4, n times 2 to the n over n cubed, and this equals 2 to the n over n squared. Right, so that's kind of like the method of what we're looking at. So because we end up with 2 to the n over n squared, we're going to choose this as our series for comparing. So choose this right? So by that I mean we're going to say 2 to the n over n squared is the series that we're comparing to. So in order, again, remember, in order to use the limit comparison test, we have to check all these kind of boxes off. So first of all, let's just state what everything is. So we are given n times 2 to the n over 4n cubed as our series, and we're comparing to n equals 1 to infinity of 2 to the n over n squared. So that means that a sub n equals n times 2 to the n over 4n cubed plus 1, and also that b sub n equals 2 to the n over n squared. So we know that a sub n is greater than 0, check, and we also know that b sub n is, greater than 0. So now what we're going to do is we're going to take the limits of the ratio a sub n over b sub n. So the next thing we're going to do is to check the limit. So we're going to take the limit, and again, it doesn't really matter who's on top and who's on bottom. I guess I'll just do a sub n over b sub n. And what's going to happen here is I get the limit as n goes to infinity of n times 2 to the n over 4n cubed plus 1. And that is going to be over 2 to the n over n squared. So I'll tidy this up a little bit. I'll get the limit as n goes to infinity of n cubed times 2 to the n on top. And then on the bottom, I'm going to get 2 to the n, well, okay, let me write it this way, 4n cubed plus 1 times 2 to the n, right? So that will be on the bottom. And now I can do some cancellation here. I can get rid of my 2 to the n's. So this will be the limit as n goes to infinity of n cubed over 4n cubed plus 1. And again, this is a really straightforward limit to evaluate, and we'll see that the limit is 1/4, which is good because 1/4 is finite and positive. So we can use this for our limit comparison. So now what we know, or where we are in the problem, is we can say that if our series 2 to the n over n squared diverges, then so does the given series. If the series 2 to the n over n squared converges, then so does the given series. So now it remains to determine whether or not 2 to the n over n squared converges as a series. So we're going to determine the convergence or divergence of this here. And for this one, we have a lot of things that we can pull from. We can do a squeeze theorem. We can do nth term divergence test. We can look at it as a known convergent or divergent series. So you kind of just have to go back into your toolkit and see what fits. For me, what makes sense here, especially because as I'm looking at this, I'm like, I know that exponential growth, which is what we're seeing in the numerator, always outpaces polynomial growth, which is what we're seeing in the denominator. So just to be clear, we're looking at exponential and polynomial. Exponential always kicks polynomials' butt. That's just a fact of life. So I'm going to use, because I suspect that this diverges, I'm going to use the nth term divergent test. So remember that the nth term divergence test just asks you to evaluate the limit as n goes to infinity of the term. If it doesn't go, if your guys inside your sum don't go to 0, there's no chance that the sum will converge because it'll just keep getting bigger and bigger and bigger. So we're going to look at the limit as n goes to infinity of 2 to the n over n squared. And I'm actually going to apply L'Hopital's rule to this. So I know, again, because exponential always dominates polynomial, I know that this is going to be infinity, but just for grins, let's go ahead and do it. So this goes to, because this is going to go to infinity over infinity, we can use L'Hopital's rule. And so we'll get the limit as n goes to infinity of the natural log of 2 times 2 to the n over 2n. And this is still going to be in the indeterminate form infinity over infinity. So I'm going to use L'Hopital's rule again. So I'll get the limit as n goes to infinity of ln of 2. Now I have 2 of those, so I can square it, still multiplying by 2 to the n. And then I'm going to get 2 on the bottom. And so since now the denominator is a constant and the numerator still has the exponential term 2 to the n, this thing's just going to blow up. So this is going to be going to infinity. So the nth term divergence test tells us that our series n equals 1 to infinity of 2 to the n over n squared diverges. So just to kind of put it all together, we had a series, we chose what we were going to compare it to cleverly, we checked the conditions, we evaluated the limit, saw that it was finite and positive, and now we're just saying, if I can say something about 2 to the n over n squared, I can say that exact same thing about n times 2 to the n over 4n cubed plus 1, the thing that we were given. And we had to do a little bit of work to make a conclusion about whether 2 to the n over n squared as a series converges or diverges. We used the nth term divergence test to show that that series, 2 to the n over n squared, diverges. And now, by the comparison test, the limit comparison test, we know that our original series also diverges. So that's the punchline. So by the limit comparison test, the series that we were given also diverges. And that's it. That's the end. Please email if you have any questions, and good luck on the homework.